Okay, so the next talk is going to be Deep Autoencoder for Combined Human Pose Estimation and Body Model Upscaling. And the authors are Matthew Trumble, Jean Collomosse, and Adrian Hilton. And the talk will be given by Matthew Trumble.
Thanks very much. Yes, I'm Matt. Hi from the University of Surrey, presenting our work towards a deep autoencoder for combined human pose estimation and body model upscaling. This work was supported by an EPSRC doctoral bursary and Innovate UK via the Total Capture project. So our aims with this work are to take motion capture out of the studio into more challenging environments, to produce simultaneous pose and body model estimation for multiple viewpoint video of open spaces, for example, in surveillance or sports footage, where the human subjects can be very small and only represented by a small number of pixels. And this can enable human behavioral analysis for performance, for sports performance, or security applications. So we're building on work from image super resolution, such as the work by Dong, applying convolutional nets to the upscaling of images, and also the 2D and 3D human pose estimation fields, such as convolutional pose machines, which perform 2D joint estimation directly from images, and Tan's work, for example, learning 3D body model shape parameters for the simple model from the Max Planck Institute of Intelligent Systems. So we developed a novel dual-loss volumetric autoencoder, inspired by autoencoders from image super resolution, but instead upscaling volumetric data up to 4 times and constraining the latent representation to give us a skeletal pose vector of the performer. The input to our network is a geometric proxy constructed from multi-view video. The camera views are converted to softmaps by background subtraction, and the capture volume is decimated into voxels, quite coarse voxels, about 6 centimeters across. And these voxels are then projected to the camera views to get a probability of occupancy from each view, and the product of these provides the overall occupancy for a particular voxel. And we visualize this on a color scale from green to red, where green is least likely and red is most likely. And so we have an input volume of 32 by 32 by 32, which is approximately 2 meter by 2 meter by 2 meter around the performer. And this is then upscaled to the target output volume size by tricubic interpolation. This is our network. It's a convolutional autoencoder with a symmetrical architecture. The encoder stage produces a pose vector of 26 XYZ Cartesian joint positions by convolution, max pooling, and fully connected layers. The decoder then inverts this process to provide a high fidelity model. We include 2 skip connections that bridge the latent representation. And these connect the output of a convolution with the corresponding deconvolution and being integrated via a mean average back into the main network. And they allow kind of high-frequency model information to bridge that latent representation. So this is the ×2 upscaling network. The ×4 network has an extra set of convolution and deconvolution layers. And as you can see, the output of the latent layer passes through an additional temporal filtering step, some LSTM layer to produce the final joint position estimate. So training proceeds by minimizing the error of the encoder and decoder outputs. So in this case, the loss function is just a weighted sum of the mean squared error values of the output of the 2 outputs. So it's the joint positions, XYZ joint positions as a vector, and then the voxel values themselves. And these are weighted to balance the relative magnitude of the 2 terms to within roughly an order of magnitude. Otherwise, one term is optimized to the detriment of the other. But within a rough order of magnitude, it's not sensitive to that factor. So as I said, the pose vector passes through an LSTM, which is an extension of recurrent neural networks. We see them a lot these days. So the aim of this is to exploit the temporal nature of human motion to improve the accuracy. And so they do this by maintaining an internal cell state controlled by gates. And we use 2 LSTM layers in sequence with a memory cell size of 1024, looking back over the previous 5 frames. So we use an internally created multi-view video human pose dataset for network training. This is available online. It was first presented last year at BMVC. It has 8 calibrated HD video cameras in a 360-degree setup over quite a large studio, and we include ground truth joint position from a Vicon system, as well as inertial data from inertial measurement units on the performer, but we don't use them in this particular work. So it comprises of 5 different subjects performing 12 different solo sequences. That's quite a big data set, quite diverse motion, walking, acting, and completely freestyle behavior. And it's split roughly 75% for training and 25% for test, including 2 completely unseen test subjects. So full details and analysis are recently published in IJCV, and it's available on our website as well if you'd like to have a look at it. So these are the results from one of the total capture test sequences, showing the ×4 upscaling. So just to say again, the color information, that the voxels are colored as indicating their probability of occupancy from green to red. So red is the most confident. I'm also showing the output pose estimate alongside compared to the ground truth. You can see it's tracking that quite well, and we get quite a convincing, realistic body model from the system too. So these are the quantitative results over the total capture data set. As I said, it's split into seen and unseen subjects. W is the walking sequences. The freestyle sequences, FS, which are noticeably a bit harder, a bit more challenging, and A for acting. As you can see, we get quite low per joint millimeter error over all of these. And we compare them to our previous work from BMVC, and also a baseline that we created using convolutional post-machine estimates from each of the camera views, triangulated into a kind of baseline 3D joint estimate to compare. So we show the full network output for the ×1, ×2, and ×4 upscaling networks, alongside the kind of raw output from a trained encoder half, so just the front half of the network. And you can see they're the benefit that we get from the LSTM and having that volumetric constraint in the training, the benefit that gives us. So this graph shows the error from the 3 different networks over the course of one example test sequence from total capture. And you can see that they track very closely with quite a low spread of error. So this is a closer look at the model upscaling itself. We're showing the input versus the ×2 and ×4 and the ground truth. The ground truth is rendered natively at that high resolution. So we can see that there's a little less voxel confidence on the borders of the model, but this could quite easily be thresholded to provide a near identical model. And one nice result from this, you can see in the middle row that the gap between the arm and the body is recovered from the input, which would be impossible from simple upscaling of that coarse input. So this is some quantitative analysis of the upscaling performance. So it shows the input and output error compared to the ground truth volume in terms of mean squared voxel error. And you can see that we're improving the error, reducing the error by about a factor of 20 compared to the input. And again, it's quite consistent over the course of a single sequence. So we also have post-estimation results for the human 3.6M dataset, which we've seen quite a lot in this conference. It's a public multi-video dataset with multiple subjects, 4 camera views, and ground truth 2D and 3D pose. And you can see again, we're recreating that pose quite faithfully, smoothly, alongside the ground truth. And these are our numbers for human 3.6. We achieve about an average of 6 centimeters per joint error, quite consistently across the different classes of the data set. And we're roughly state-of-the-art with comparable approaches that we've listed there. So we did some further cross-validation testing on the human 3.6 data set. This is just to hold out a different pair of test subjects from for each fold of the testing, just to see how consistent our performance was. And we get quite a consistent performance with a low spread of errors, which is nice to see. Again, about averaging that same kind of 6 centimeter error mark. So we had made an addition to the total capture data set called Total Capture Outdoor, which is a much more challenging data set. We're outdoors now, we're out of the studio. So there's changing lighting conditions, moving backgrounds, a much larger capture volume, in this case about 10 by 10 meters. And we have, this time, just 6 cameras in a 120-degree arc, so we don't have full 360-degree coverage. And we get, we think, quite surprisingly good results from these very challenging conditions, quite convincing body models, and realistic pose from that as well. So this shows the output from one frame, the upscaling kind of rendered from different viewpoints, just to show that we can convincingly generate those novel viewpoints, because the input is only a 120-degree arc. We don't have full coverage, but the models are still quite consistent view from all angles, which opens up possible applications in VR, AR, and film and sports post-production. So just to summarize, we've developed a novel 3D dual-loss autoencoder with real-time inference from multi-view HD video. We perform simultaneous 3D pose and body shape estimation from very coarse volumetric shape data, and we get quite surprising accuracy from that coarse input. And we can generalize well to the unseen subjects in our test data. One limitation would be that we do rely on a good initial segmentation to get that initial coarse volumetric estimate. And as I said, the dataset is available online on our website. If you're interested, please do check it out. Thanks very much.
Thank you for the talk. Questions? Okay, so let me start with one. So all the results you've shown, like the motions that are reproduced, are relatively articulated. So do you think you could use this method to reproduce non-rigid deformation, for example, people wearing skirts or jackets? Do you think it would work?
Well, I think obviously that depends on the training data that you've got. The training data that we've got at the moment is, I guess, we're limited by the Vicon ground truth. Requires quite tight-fitting clothing for that system to work. So we haven't tested it on more challenging clothing like that, so it's hard to say. But I think it'd be interesting to see how it performs with those much harder input models. But we don't really know exactly how that would work out.
Mm-hmm. Thank you. More questions? Maybe I have another question then. So right now, your network can upscale like a probabilistic volumetric representation. Do you have any thoughts on how to go from a skeletal pose to directly the 3D volume without needing the skip connections?
Yeah. That would be a nice development to somehow maybe transfer that information through the latent representation. Mm-hmm. Maybe some kind of like we've seen in Rodin Helga's work, where the appearance of information is part of the latent representation. That would be a nice addition, and then that could be used as a purely generative kind of layer. Mm-hmm. That would be a really nice development direction for it to work, yeah.
Okay, so if there's no more questions, let's thank the speaker again.